Okay, thank you. My name is Zhang Gu. I'm from Stats Department. I'm a fourth-year PhD student. And my topic today is to introduce you a R package we wrote ourselves, the Sparsebn package. It can do structural learning of large-scale Bayesian networks. Okay, so first, the outline for today is that I will first introduce the main features of our package, then followed by the methodology we used, and followed by some examples to walk you through all the main features. And finally, I will tell you where can we download the package. Okay. And for the features of the Sparsebn package, we have a very competitive performance for high-dimensional dataset. And also, like many other structural learning packages, our package can learn continuous and discrete networks. When for continuous case, that all the random variables follow a joint multivariate normal distribution, the Sparsebn package is very fast. It can handle datasets with P potentially in thousands of variables. And our algorithm is actually over 100 times faster than existing methods, such as the popular PC algorithm and MMHC algorithm, while still achieving a comparably the same or better performance. And one thing that makes our package more unique is that we can learn a mixture of observational and interventional dataset. While I think for the PC algorithm and MMHC algorithm, they can only learn observational dataset. Moreover, our package provides method that can do empirical model selection and also a method that can do parameter estimation, so users can do inference after they got the structure of a network. And finally, our package is compatible with 3 widely used graphical packages. They are iGraph, Graph, and the network. So users can very easily create beautiful plots. Okay. And for the methodology we used in our package, we used a scoring-based method to find a sparse stack that will minimize a negative log likelihood with a penalty. The penalty we used in our package is either a lasso penalty or a minimax concave penalty. The users can specify the option. So instead of getting a single estimation, our package will give the users a sequence of estimated DAX, and that will form a solution path. And the algorithm we used is a coordinate descent algorithm. The outline of algorithm is here, and due to the time limit, I think I don't have any time to go into any details of this algorithm. So I have mentioned, for continuous case, our algorithm can be very fast. So this is a comparison between the running time of our CD algorithm compared with the PC algorithm, the blue one, and the MMHC algorithm, which is the green one. So we can see that when the number of nodes become large, when it exceeds 1,000, our CD algorithm can still be very fast, while the PC algorithm and the MMHC algorithm actually takes much more time. However, these results only constrained to Gaussian dataset. So for a discrete dataset, our algorithm will not be this fast, and we're still working on it to make it faster. Okay, now let me first show you a very simple example for the main feature of our package, that is the structural learning part. So Pathfinder is a network with 109 variables, and this dataset is a continuous dataset with only observational data. So before we feed the data into our algorithm, we will need to first transform the dataset to the Sparsebn data object. We can easily construct this object by specifying the data frame or the data matrix and the type of data, which is continuous in this case. And now we can feed the Sparsebn data object into our algorithm. And here is an example to plot the first 5 DAGs along the solution path. Notice that here are only 4 because the solution path always starts from a null graph, so our package just skip it. And now we have a more specific example on the flow cytometry dataset. This is from a network of human immune system. And for this network, it has only 20 variables. So it's easier for us to show, it's easier for me to show our results. So firstly, we will need to load the dataset. Our package provides both the continuous case and the discrete case of this dataset. And please note that the flow cytometry dataset is a mixture of observational and also interventional data. So in addition to specify the data matrix or data frame and the type, we should also specify a list of intervention. Today, the example will focus on the continuous case. Okay, so after we feed the transformed dataset into the algorithm, the CD algorithm gives us a solution path consists of 20 nodes. So the result get by this estimate DAG function is a S3 class. It's a Sparsebn path object, and it's also a list. So each node along the solution path is a Sparsebn fit object, which contains the following information. Firstly, it's the edge list, and it's the number, it's the name of the nodes, the value of the lambda, the number of edges, the number of variables, the number of observations in the dataset, and also the time for our CD algorithm to run to get the estimation of this specific DAG. And we also provide a very handy way to extract the adjacency matrix from a Sparsebn fit object. And please note that all the matrix stored in our package used a sparse representation, so we can save some memory. Also, it's easy for us to get the parent list for each DAG estimated by our algorithm. And this is an example for the DAG we estimated. This is the 7th DAG along the solution path. And also, I have mentioned that our package is compatible with iGraph, so it's easy to use argument in iGraph to create nice and clean layout of the output graph. Now, this is an example to output the 7th DAG laid out in a circle. So users who are familiar with iGraph or Graph or the network package will find that our package very easy to do all the plots. And we have also provided a parameter estimation method. So after we got the structure of a DAG, we can use this parameter estimation method to do inference. And for continuous case, if we feed the estimate parameters function with a solution path and the dataset, it will automatically estimate the parameters for all those 20 DAGs along the solution path. And since now we have a continuous dataset, we will have the coefficients, which is the weights of the matrix, and also the variance of the variables. And finally, we provide two different parameter selection methods. The first one is quite naive. This select method will return a selected Sparsebn fit object, and we can do the selection by matching edges or by matching the value of lambda, or just simply specify the index. And also, we can use an empirical model selection method. So this select parameter method will return the index of a selected DAG. So it will return the DAG that we think will be the optimal along the solution path. And you can use this select function matching the index to get the Sparsebn fit object. And finally, since our package is on CRAN, so you can just use install packages to download our package. And we have a paper that have more technical details and more specific manual. This is the Learning Large-Scale Bayesian Networks with the Sparsebn package. Now it has posted on archive. Okay, and that's all for the package today. Any questions?